Hello and welcome to part 2 of Chapter 8, Concepts of Chemical Bonding. Today we're going to start out looking at section 8.4, which deals with bond polarity and electronegativity. And to start out with, we're going to start out by looking at polar covalent bonds. When we look at two atoms that are identical and something like we have F2 right here, or fluorine, in the case of a diatomic molecule, we know that the electrons are being shared equally. Now, this is not always the case. So it says, though atoms often form compounds by sharing electrons, the electrons are not always shared equally. Now, when we look at the case of hydrogen and fluorine together, fluorine is going to pull harder, or fluorine is going to want those electrons even more so than hydrogen is going to want them. So therefore, we say the fluorine end of the molecule has a more electron density than the hydrogen end. And that's because if you think about it, if fluorine is going to be fighting or pulling more, it's probably going to get more of the electrons, and those are going to be kind of hanging out at the fluorine side of things, to where hydrogen is going to kind of have a less dense area because there's going to be fewer electrons hanging around the hydrogen side. So before we continue on, I want to kind of clarify a couple terms. The first one is being bond polarity. Now this is, when we talk about bond polarity, this is talking about the whole concept of sharing electrons. When we're talking about nonpolar covalent bonds, this is when our electrons are being shared equally. And so if you think about it, nonpolar means that there's not going to be a charged end, polar meaning charged, okay? So nonpolar means that there's not a charge on either side, so everything's being shared equally in the case of the fluorine atoms. Polar covalent, however, means that there's going to be a greater attraction on one side than there is the other side. So we say polar covalent bonds occur when one of the atoms exerts a greater attraction for the electrons than the other atom does. And when we're talking about all of this nonpolar and polar covalent bonds, we get a term that comes up as electronegativity. Now, electronegativity is very, very similar to electron affinity and ionization energy. However, electronegativity is the ability of an atom in a molecule to attract electrons to themselves. So on the periodic chart, like the ionization energy and electron affinity, we actually have trends. So when we're looking at electronegativity tends to increase as we go from left to right across the row, and as we go from the bottom to the top of a column. Or if you want to think of it from top to bottom, it's going to decrease as we go from top to bottom. And you can look at this table right here. It kind of shows you the trends, gives you some numbers. You do not have to memorize the numbers. You do have to know the trends, however. So again, just to reiterate, because these three terms are very close in meaning, electronegativity is the ability of an atom in a molecule, and we have to stress molecule, to attract electrons to itself. Ionization energy measures how strongly a gaseous atom holds onto its electrons, and electron affinity measures how strongly an atom attracts additional electrons. When two atoms share electrons unequally, we say that a bond dipole results from that. And we get a dipole moment, and the symbol didn't come through, but in this box here, we should have had the Greek letter mu, M-U, which kind of looks like a fancy little U. And this is produced by two equal but opposite charges that are separated by some distance r. And we can actually calculate this dipole moment by taking using the equation mu equals Q times R. And Q, if you recall, is our charge. R is the distance between the two molecules. And we say that this is measured in dBs, which is represented with a capital D. You will also need to know that 1 dBs is equal to 3.34 times 10 to the negative 30th coulomb meters. So again, just to reiterate, the greater the difference in electronegativity, the more polar the bond is going to be. And that's because if you want to think about it in terms of charges, your charges, if I have something that's more polar, it means it's going to have a bigger pull from one element than the other. Now, something that you may notice too as you read your textbook or do your web assign, if we look at hydrogen and fluorine here, they're bonded together by a covalent bond, so they're sharing. Sometimes you'll see a little symbol that looks like this kind of fancy curly little S, and hydrogen is actually going to be slightly positive because the fluorine is kind of pulling more of the electrons its way, which then means that fluorine then is going to be slightly negative. Now this fancy little S is read as delta, okay? It's a Greek letter for delta, okay? And we say delta plus or delta minus. And what that means is it means that there's a really small change in the polarity. So as we mentioned, fluorine is going to want the electrons more than hydrogen, so they're going to be kind of drawn closer to fluorine. So fluorine is going to be slightly negative in charge, and the hydrogen atom then is going to be slightly positive in charge because the electrons are kind of leaving it a little bit. Same thing when you look at hydrogen chloride or hydrogen bromide or hydrogen iodide. However, if you remember the trend in electronegativity, we tend to decrease as we go from top to bottom, and with fluorine being at the top and iodine being at the bottom, that's why iodine or hydrogen iodine is less electronegative than hydrogen fluoride. So, when we look at example 4, it says in each case, which bond is more polar? Which atom has a partial negative charge? So if we look at the boron chlorine or the carbon chlorine bonds, we need to identify which one is more polar. And to do that, we have to identify which is more electronegative. So because chlorine is a common atom in both, we really have to look at the comparison between boron and carbon. Now when we look at our periodic table, boron is to the left of carbon on the periodic table, so we can predict that it has a lower electronegativity. And the more polar bond then will go with the one that has the lower electronegativity. Therefore, the boron chlorine bond is a more polar bond, and the chlorine atom is going to take the partial negative while the boron is going to take the partial positive. So now we're going to go through the same process for part B, where we're dealing with phosphorus and fluorine or phosphorus and chlorine. Again, phosphorus is our common atom, so we really need to look at the differences between fluorine and chlorine. And because fluorine appears above chlorine on the periodic table, we know that it's more electronegative. Therefore, the polar bond is going to occur with the fluorine and phosphorus bond then. So we actually have the phosphorus-fluorine bond, and because fluorine is more electronegative, this is going to take on the partial negative, while phosphorus takes on the partial positive. Now example 5 says the bond length in the HCl molecule is 1.27 angstrom. We want to calculate the dipole moment in Debye that would result if the charges on hydrogen and chlorine atoms were plus and minus 1 respectively. So the first thing we're going to do is we're going to use that equation mu equals Q times R, and we know that the charge of an electron, the charge being plus or minus is actually going to come from the electron. So that's our Q value. Well, Q is really equal to the charge of the electron. So in this case, our Q is going to be 1.602 times 10 to the negative 19th coulombs, which is represented with a capital C. This is on your blue chart that you're given for your test and on the AP test. Our radius is given by the angstrom, which is 1.27 angstroms. Now we do have to convert that, however, to meters. And to convert that to meters, we're going to multiply that by 1 times 10 to the negative 10 angstroms for meters for every 1 angstrom. So we've converted that. And then we need to take this answer, which we've actually canceled out, our angstroms, and we're left with coulomb meters. So because we're looking for a dipole moment, we need to get our answer in units of Debye. So to convert to that, we need to use that conversion factor that was given to you a couple slides ago that said 1 Debye is equal to 3.34 times 10 to the negative 30th coulomb meters. And what you should see now is your coulombs are going to cancel, your meters are going to cancel, and we're going to be left with our unit of Debye. And when we multiply everything through, we end up with 6.08 Debye. Now for part B, we are given that the experimentally measured dipole moment of HCl is 1.08 Debye. We want to know what magnitude of charge in units of E on the hydrogen and chlorine atoms would lead to this dipole moment. So in other words, if we look at our equation that we used up above, where we have mu equals Q times R, we're looking for the Q value. So in order to solve for Q, we're going to rearrange our equation, and we get mu divided by R. So to simplify this, our mu value is going to be our Debye. So we have 1.08 Debye, and we have to convert that. So we're going to multiply that by 3.34 times 10 to the negative 30th coulomb meters for every 1 Debye. And then we're going to divide by our distance, which is the 1.27 angstroms. And we also have to convert that. So we're going to multiply that by 1 times 10 to the negative 10 meters per angstrom. So when we do a unit check, our Debye are going to cancel, angstroms are going to cancel, and our meters are going to cancel. This is going to leave us with 2.84 times 10 to the negative 20th coulombs, which would be fine, except it wanted my magnitude in units of E, or electronic charge. So I'm then going to take that answer that I just got. So I have my 2.84 times 10 to the negative 20th coulombs, and I'm going to convert using the conversion that 1E is equal to 1.60 times 10 to the negative 19th coulombs. So now when I simplify, I end up with 0.178 E, or electronic charge. The next thing we're going to look at is Lewis structures. Now, Lewis structures are representations of molecules that are showing all electrons that are bonding and non-bonding. So in order to write our Lewis structures, we actually have a series of 5 things that we have to look at. The first thing says to find the sum of the valence electrons of all atoms in the polyatomic ion or molecule. So when we look at this example here for phosphorus trichloride, phosphorus has a valence, or has 5 valence electrons, and chlorine has 7 valence electrons. However, there are 3 chlorine atoms. So I have to go 3 times 7 and add my valence electrons together, and I get a total of 26. If you have an anion, we're going to add 1 electron for each negative charge. If you have a cation, we're going to subtract 1 electron for each positive charge. The next thing we're going to do is we're going to look at the central, or try to figure out which central atom, or which atom is in the center of all of the atoms that are given. So we're going to do that by taking the least electronegative element that is not hydrogen. Then we're going to connect the outer atoms to it by a single bond. And again, we have to keep track of the electrons. Then, if you'll notice right down here, we still have to keep track of our electrons. And because I have 6 electrons that are being shared, I'm actually going to subtract that from my initial total that I just counted out. So I have 26 minus 6, which gives me 20. Then I want to fill out my octets. So I have 2 electrons here, and I need 6 more around chlorine. So I have 2, 4, 6, 2, 4, 6, and then don't forget that a single line counts as 2, which is 8. Then I need to subtract all of my outer electrons, or my unpaired electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm going to take my 20, subtract 18, and I see that I have 2 electrons left. Then I need to fill the octet of the central atom. So that means I'm going to go and I'm going to place my 2 electrons here. So I have 2, 4, 6, 8 electrons now on phosphorus. And when I take those 2 electrons that I just added to phosphorus, I'm going to subtract those from my initial 2, and I see that I get a subtotal of 0. And this is exactly what I want. I need my atom to, or my molecule to be neutral, so I need to end up with a charge of 0. Now, in the event that you run out of electrons before your central atom has an octet, this tells us that we're actually going to have multiple bonds. And we're going to continue to form multiple bonds until we have a balanced octet for all of our elements. The last thing we have to do is to assign formal charges, because sometimes you can do many different arrangements when we are doing Lewis structures that will fulfill an octet rule. However, there's only going to be one ideal molecule or polyatomic ion. So in order to figure out which arrangement is best, we actually need to assign formal charges of any atom in a molecule. And we're going to do this kind of based on the assumption that if all atoms in the molecule had the same electronegativity, so we have to assign electrons to atoms kind of in the following manner. The first thing we're going to do is we're going to count the electrons in the lone pairs and half the amount of electrons that are being shared. So if we look at the example right down here, we see that we have 6 valence electrons on oxygen, 4 on carbon, 6 on oxygen. Now, when we look at the electrons that are assigned to the atom, again, we're going to start out with our lone pairs. So I see that I have 2, 4 in my lone pairs, and then I have 2 pairs in each bond here, which would technically give me 8, but I'm going to take half of that, or I'm sorry, would technically give me 4 electrons here, but I'm going to take half of that. So I'm going to go 2, 4, and then half of 4, which would be 2, which is going to give me another 6. Same thing on carbon. Carbon has 2 sets of double bonds, which means that it's sharing a total of 8 electrons. Now because they're being shared, I'm going to take half of that, which gives me 4. And then I'm going to do the same thing again with oxygen, which will be just like the first oxygen. I have 2 lone pairs, and then I'm going to take half of the shared ones. So I have 2, 4, and then another 2 is 6. And then I'm going to subtract the valence electrons from the assigned electrons, and that's going to give us our formal charge. So in this case, you can see that we're going to get a formal charge of 0. However, if we come over here and we look at oxygen, carbon, and a triple bonded oxygen, we'll see that we have 6, 4, and 6 for our valence electrons. But this time, when I look at my oxygen, I have 2, 4, 6 lone pairs plus 1 electron here, which gives me 7 electrons. Carbon still has 2, 4, 6, 8. Half of that is going to give me 4. And this oxygen here has 1 set of lone pairs for 2 electrons, plus half of 6, which is going to give us 3. So 2 plus 3 is 5. When I subtract these values out, I get a -1 and a +1. So what you'll notice is that when we add these two together, we also get a net charge of 0. So now we have to decide which one is the correct structure. So in order to tell, we're going to take the one with the fewest charges, or the one that puts a negative charge on the most electronegative atom. So based on these two rules and thinking back to the previous example, we're going to actually take the first setup that looked like this, because this did not have any charges, so I had the fewest amount of charges. So based on the first rule here, we can say that this right here then would have been the correct Lewis structure. And before we end this, I just want you to keep in mind that a formal charge does not represent the real charge of an atom. So please don't think that that has any bearing on this. Now, real quick, if you would take a second and try to calculate out of these three structures, which one would have the correct Lewis structure, and I know it is circled, but I want you to tell me why this one would have a correct Lewis structure versus these. I will check to see that you've attempted this. So on that note, have a good night, and we'll see you tomorrow in class.